indirect proof is also called proof by contradiction. The official definition of an indirect proof, according to the book, is an indirect proof. In an indirect proof, you start by making the temporary assumption that the desired conclusion is false. By then showing that this assumption leads to a logical impossibility, you prove the original statement true by contradiction. There are different types of proofs we learned so far. We've learned algebraic proof, geometric proof, a coordinate proof in 5.1, and now we're going to be learning about indirect proof. An indirect proof basically is, the goal of an indirect proof is to find a contradiction. And an example of that would be as follows. Here we are given that x is an odd number. We need to prove that x is not divisible by 4. So the way you do a proof by contradiction or an indirect proof is you first assume the opposite of what you're trying to prove. So here in the proof statement is x is not divisible by 4. So what you would do is assume that x is divisible by 4. And then once you assume that, you try to find a contradiction. So in step 1, you would assume temporarily that x is divisible by 4. This means that x divided by 4 equals n for some whole number n. So multiplying both sides by 4 gives you x equals 4n. So in other words, we're going to turn this statement first into its opposite. The opposite of that statement would be x is divisible. I'm going to put the abbreviation div for divisible. X is divisible by 4. And then we're going to express that in a number sentence. So x divided by 4 equals n is the equation that describes the statement x is divisible by 4. We want to get x by itself, so you multiply both sides by 4 and you get x equals 4n. Now, based on this statement or equation, we need to show a contradiction. We are given that x is an odd number. So, in step 2, we see that if x is odd, then by definition, x cannot be divided evenly by 2. So x is an odd number. That means x cannot be divided by 2. However, according to step 1, x equals 4n. So if we divide x by 2, we're really dividing 4n by 2. 4n divided by 2 is 2n. We know that 2n is a whole number because n is a whole number. So x can be divided by 2. This contradicts the given statement that x is odd. So we first assumed, again, that x is divisible by 4. We wrote an equation to express that. X divided by 4 equals n. And then we solved for x and got x equals 4n. We divided 4n by 2 and got 2n. 2n is an even number. If you plug in any number to n, you're always going to get an even number. If you plug in 5, you get 10. If you plug in 7, you get 14. If you plug in 2, you get 4. So no matter what number you plug in for n, because you're multiplying it by 2, you're going to get an even number, and that's a contradiction because you were given that x is odd. Therefore, in step 3, we can say that the assumption that x is divisible by 4 must be false, which proves that x is not divisible by 4. So that's why it's called an indirect proof. It's a roundabout way of showing that what you're trying to prove is actually true. You first assume the opposite, then show a contradiction, and then you can conclude that the proof statement is actually true. So in your notes, what you want to copy, is these 3 key steps for how to write an indirect proof, or also known as proof by contradiction. Step 1. Identify the statement you want to prove. Assume temporarily that this statement is false by assuming that its opposite is true. Step 2. Reason logically until you reach a contradiction. Step 3. Point out that the desired conclusion must be true because the contradiction proves the temporary assumption false. So I'll give you a moment. You can pause the video to copy these 3 steps. Okay, moving on. So let's do a guided practice. Suppose you wanted to prove this statement: if x plus y is not equal to 14 and y equals 5, then x does not equal 9. What temporary assumption could you make to prove the conclusion indirectly? So again, the first step is to make a temporary assumption that the conclusion is true. So here it says that x is not equal to 9. So the first step, you would suppose that x is equal to 9. And let's see what happens if we make x equal to 9. Step 2, we're going to plug these numbers in to see if we find a contradiction. So we have x plus y not equal to 14 is our given statement. And they also gave us that y equals 5, so we're going to go ahead and plug that in and rewrite the rest of the equation. Now x, we assumed it equaled 9. 9 plus 5 is 14. This statement, when we plug in 9, reads 14 not equal to 14. Well, we know that obviously is false because 14 is equal to 14. But this statement is saying 14 is not equal to 14. So we found our contradiction. So when we assumed that x equals 9, we found a contradiction. That means that x cannot equal 9. And that means that this conclusion is actually true. So step 3 would be saying x does not equal 9 is a true conclusion. Okay. Now we're going to use this indirect proof to prove the converse of the hinge theorem. We need to write an indirect proof of the converse of the hinge theorem. We are given that AB is congruent to DE, BC is congruent to EF, and AC is greater than DF. We need to prove that the measure of angle B is greater than the measure of angle E. So we're going to do proof by contradiction. First, we are going to assume the opposite of the conclusion, or the proof statement. The proof statement says the measure of angle B is greater than the measure of angle E, but we're going to assume that the measure of angle B is not greater than the measure of angle E. So notice it's a greater than sign with a line through it. That means not greater than. Then it follows that, so if the measure of angle B is not greater than the measure of angle E, then two options are only left. Either the measure of angle B is equal to the measure of angle E, or the measure of angle B is less than the measure of angle E. Let's see what happens in those two cases. Case 1. If the measure of angle B is equal to the measure of angle E, then the angles are congruent, and that would make these two triangles congruent by SAS. So if these angles were equal, notice it's side, angle, side. and side angle side. Now, that's not what we're trying to prove. We're trying to prove that this angle is actually greater than that angle. But the contradiction in this case would be if these two triangles are congruent, that means that AC is equal to DF. What's the contradiction there? If you look at the given, we were given that AC is greater than DF. So the measure of angle B cannot be equal to the measure of angle E because it would contradict the given information. If these were equal, it would make the triangles congruent by SAS, and it would make AC congruent to DF, which contradicts our given. So case 1, we found a contradiction. Let's look at case 2. In case 2, if the measure of angle B was less than the measure of angle E, then AC would be less than DF by the hinge theorem. And that also contradicts the given information. The given tells us AC is greater than DF. So both conclusions contradict the given statement that AC is greater than DF. So the temporary assumption that the measure of angle B is not greater than the measure of angle E cannot be true. This proves that, indeed, measure of angle B is greater than the measure of angle E. And that's it for part 2 of 5.6.